Lesson 6.2 reminds us of the properties of rational exponents, which, by the way, are exactly the same as they were when they weren't fraction exponents. And it also helps us use these properties to simplify like terms and to know what a like term is. So for starters, let's get our vocab down here. It starts with the simplest form of a radical. There's a lot of words here, but all you really need to get down in your notes is to know that when you have a radical in simplest form, there is no perfect nth term as a factor. So what that means is none of the lists of the perfect square on the wall or perfect cubes on the wall or perfect fours on your cheat sheet would be able to go into the number that's under the radical sign. So for example, if we have the third root of, let's say, 16, that's not simplified because 8 would go into 16 and it has a third root. So that's what simplest form means. Like radicals are exactly what it says here, two radicals or two roots that have exactly the same index on the root and base under the radical sign. That's what a radicand is, the number that's being used as a base. So the properties of rational exponents, they go exactly the same as the properties we had before. Notice if you have the same base, as we do here with the a, and they each have their own exponent, what we can do with those exponents is add them. So if we have the same base 4, and they each have an exponent, we would add those exponents and put them on the 4. So 1/2 plus 3/2 is 4/2. 4/2, of course, is 2. Go ahead and simplify that. You get a 16. The next property we have has to do with the power to a power. If we have one base with two exponents, we multiply those exponents. So here we have the base 2 with two exponents. It shows that we're multiplying those exponents. Remember how to multiply 5/2 times 2. Put it over 1, cross out the 2's. That means you're going to get 2 to the 5th. Simplify that, and 2 to the 5th is 32. And then the next property we have is if you have a parenthesis with exponents. Like we have always done, we need to distribute that exponent to everything in the parenthesis. So the 1/2 goes on the 16, the 1/2 goes on the 4. Now remember what 1/2 means, it just means square root. So the square root of 16 is 4, the square root of 4 is 2. Those two things are multiplying each other, so we get an 8. Next we have the negative exponent, and as always, negative exponents mean you need to move it. So in this case, we're going to move it to the denominator. It becomes positive. Remember that 25 to the 1/2 simply means the square root of 25, which is 5. When we have fractions and we're dividing, we still can subtract those exponents when they have the same base. So here we have a base of 3 on top, a base of 3 on the bottom. So if we're going to simplify that fraction, we would subtract those exponents. So we'd end up with 3. 5/2 minus 1/2 is 4/2, and 4/2 is 2. So 3 squared, we're going to get a 9. And finally, if we have a fraction with one exponent, we need to make sure that exponent goes to both the numerator and the denominator on the fraction. So here we have a 27. It gets the 1/3. And we have an 8. It gets the 1/3. So the 1/3 exponent means we're taking the cubic root. The cubic root of 27 is 3. The cubic root of 8 is 2. So all of the properties we have still hold true. We just have to deal with them with fractions, and that's probably what makes it a little more difficult, is we're just not maybe as comfortable dealing with adding and subtracting fractions. Let's take a look at our example 1. We have the same base 9, and as long as we have the same base 9, we can add the exponent 1/2 plus 3/4. All right, so here's our challenge. We got to know what 1/2 plus 3/4 is. Well, if you need to, grab your calculator. If not, you know that 1/2 plus 3/4 is 5/2. Now, we're not quite done there. Oops, wait. I did that wrong. 5/4. Okay, we're not quite done there because maybe this will simplify, because remember 5/4 is the 4th root of 9 to the 5th power. But if you try that and type it in your calculator, you're going to find out you come up with some ugly decimal, so we are done in that case. If you wrote this as your answer instead, it is the same answer. Both answers are correct. The next one, we have a 3 outside the parentheses, so that 3 needs to get distributed to both exponents inside the parentheses. So 7, 3 times 2/3 is 2, times 5, 3 times 1/6 is 1/2. Okay, what is 7 squared? Well, 7 squared is 49. What is 5 to the 1/2? It's 5 to the 1/2, or the square root of 5. Same base in letter C, so we can subtract the exponent. Does that mean we'd have 3 to the 5/6 minus 1/3? 5/6 minus 1/3, which is 2/6. So 5/6 minus 2/6 is 3/6, and 3/6 is 1/2. 3 to the 1/2 is an answer in rational form, and the square root of 3 is the answer in radical form. Next, we have a fraction that has a 4 to the outside. Now, there's a couple of ways we could look at this thing. First of all, if you notice that these have exactly the same exponent on them, that means they have the same radical index. We could start this whole thing by dividing, because these two exponents are the same, and we could write this as 4 to the 2/3 all to the 4th. All right? Now, if we do that, then we have to put that 4 inside because we have an exponent on top of an exponent. We multiply. We'd have 4 to the 8/3. That could be our final answer, or we could write it as the cubic root of 4 to the 8th power. All right, then we're going to move on to radical properties. We just covered all of the exponent properties. Radical properties we have to know as well, because radicals and exponents go hand in hand. Well, if we have the nth root of a times b, we can break that up into the nth root of a times the nth root of b. That's one of the properties. We can break up radicals. We can also break up radicals that are written as fractions the same way, the nth root of a over the nth root of b. So in example 2, we're supposed to use these properties to try and simplify the radicals, and that's why you have your cheat sheet. That is going to help you simplify these, because you probably don't know all the perfect cubes and perfect 4s and perfect 5s, as well as you know all of the perfect squares. They're listed on the board, the cubes and the squares, but the 4s and the 5s are on your cheat sheet, so that's why I'm having you grab that at this point. If you don't have it out, take that out and keep it out. You're going to need it most of the day. So if I look at this problem, there's a lot of ways I could start it. I could check and see if 27 has a 5th root. It does not. 9 does not have a 5th root. So the next thing I'm going to do then is I'm going to combine those to 27 times 9, which happens to be 243. Well, now what I'm looking for is the 5th root of 243. On my cheat sheet, I'm going to look in the 5th column, because that's where my perfect 5s are. I see there is a 243 there. So the 5th root of 243, following it over to the left, is a 3. In letter B, I have the cubic root of 192 divided by 3. Well, the cubic root, 3 doesn't have a cubic root. So what I'm going to do instead is put those two together under 1 root and have 192 divided by 3. 192 divided by 3 is 64. So if I look for the cubed root of 64, I can either look up on the wall or I can look in my cheat sheet. Either way, the cubic root of 64 is 4. Go ahead and try and simplify both of these expressions. Put me on pause and then come back and find out how I worked it. A couple of different ways you can approach this one. If you distribute that exponent to both pieces, you would have 6 to the negative 1 times 5 to the negative 1. Well, that means they both have to move to the bottom, so 6 times 5, and 6 times 5 is 30, so you get 1 over 30. The second one, the square root of 5 doesn't exist, so instead I'm going to think of this as 245 divided by 5. And 245 divided by 5 is 49. The square root of 49 is 7. Okay, now, of course, all radicals don't simplify out to just a whole number. Sometimes there's some radical left, and that's what's going to happen in these next ones, but we're going to use the same procedure we used when we were simplifying square roots. It's just that now we're simplifying the fifth root. Well, the first thing we're going to look for is we're going to look for any factors that are perfect fifths that go into 128. So I'm looking at my last column of my cheat sheet, and I notice that 32 goes into 128 4 times. So I can write this as the fifth root of 32 times the fifth root of 4. And again, the reason I chose 32 is because 32 is a perfect fifth. So the fifth root of 32 is the whole number 2. 4 doesn't have a fifth root, so I'm done. My answer is 2 times the fifth root of 4. All right, now that's the only example of breaking it up there. This is the only example of rationalizing the denominators. You might have to go back and replay this more than once to understand it. Here's what we're going to do with this one. If I break this up, I have the cubic root of 5 over the cubic root of 9. Well, I can't leave a radical in the denominator and be simplified. So what I'm going to do is I'm going to multiply that denominator by some other cubic root that will make a perfect cube. The reason I want a perfect cube is because I'm taking the cubic root. So I'm going to look at my cube list and think, what can I multiply 9 by to get something in my perfect cube column? Well, I notice there's a 27 there, so I could just multiply it by the cubic root of 3. But whatever I do to the bottom, I have to do to the top. Now, let's see what happens. Well, on the bottom, I have the cubic root of 27. And on the top, I have the cubic root of 15. Okay, look at the bottom. What is the cubic root of 27? It's the whole number 3, so mission accomplished. I was trying to get the bottom to not have a root any longer. The top is the cubic root of 15, which I don't care if there's roots on top. It just can't be on the bottom, so I'm done. That's the most you can do with that one. Okay, we'll get some more simplifying practice in these problems because you're going to have a lot of simplifying practice on your homework, and there wasn't too much of it really in your note guide. So let's look at example 4, and then we'll come back and do checkpoint 4. This one says to add and subtract like radicals and roots. Well, remember from our vocab words, we said that like radicals had to have exactly the same index and exactly the same radicand, which means base. So I'm looking at these two things and I'm thinking, well, this has a base 12, this has a base 12, so we've got that covered. This has an exponent of 2/3, this has an exponent of 2/3, so we've got that covered. They're the same. Now you have to think of this kind of as apples and apples. If I asked you how many apples do you have right here, hopefully you can see that you have 2 of them. If I asked you how many apples we've got right there, we have 7 of them. So if I'm adding them together, I'm going to have 14, but they're still apples. So I'm going to write this as 12 to the 2/3. Now, if you really prefer radical language instead, or if that's what the answer key has, this would be 14. We'd have the cubic root, because 3 is on the bottom, of 12 squared, all right, or the cubic root of 144. You can leave it as 12 to the 2/3, or, oh my goodness, I can't believe I just did that whole thing. Yes, if all of you are hollering and saying, no, you just said we're adding. 2 plus 7 is not 14, it's 9. Sorry, I'm trying to do this too fast. So you get 9 times 12 to the 2/3. So go back and make that correction. All right, the next one, we are adding and subtracting. So look at my base is 48 and my base is 3. Well, there's nothing we're going to do if we have a base of 48 and a base of 3 because they are not like terms. However, we've learned how to simplify. So let's take a closer look at this fourth root of 48. Well, does 48 have any perfect 4s that go into it? It does. 16 goes into 48. So I can rewrite this as the fourth root of 16 times the fourth root of 3, because 3 times 16 is 48. Fourth root of 3 doesn't change at all, so I'm just going to write that down. Now, what do I really have here? Well, the fourth root of 16 is a 2. So I have 2 fourth roots of 3 minus, this would be 1 fourth root of 3. So again, if you think about, I have 2 apples minus 1 apple. What do I have? I have 1, but they're still apples. They stay exactly as they were before I added or subtracted them. All right, number 4. I made it almost too easy. You're supposed to add like terms. You probably don't even have to pause it, because how many total are you going to get? Well, you have 6 here, plus you have 2 there. That makes it 8. But remember, these have to be identical. They are. And if you had 6 of one and 2 of the other, you're going to have 8 total, but they stay the exact same expression. 6 apples plus 2 apples are 8 apples. All right, so now let's move into variables. How are you going to simplify when you have variables? Well, what I always do when I have variables is I think if all else fails, convert everything to fraction exponents, and all of a sudden the variable problems don't seem quite so hard. So I'm going to separate off, and first of all, I'm going to deal with the fifth root of 32. And then second of all, I'm going to deal with the fifth root of x to the 15. I like to treat my numbers separate from my variables because it just seems to make more sense and it's easier to deal with. So first of all, I'm going to look for the fifth root of 32. If I get lucky, it's a perfect fifth, and I can get an answer right away, and I do. It's 2. Now, this fifth root of x to the 15. Just think about what that would be if I change it into a fraction exponent. My exponent is 15. My index is 5, or my root is 5. Well, look what you have. You have x to the 15 over 5. That's just x to the third. So your answer is 2x to the third. Okay, the next one. We have to, first of all, distribute this 1/2 to everything. Don't forget about the 36. So we have 36 to the 1/2. We have m to the 4 times 1/2, which is 2. We have n to the 10 times 1/2, which is 5. That's the first step. Now, what is the half root, and not half root, what is 36 to the 1/2? 36 to the 1/2 is 6. We already have the m squared simplified. We already have the n to the 5th simplified, and we are done. Now remember, we are multiplying here, and multiplying you can pretty much do to anything. It's when you're adding that you have to make sure you have the same base and the same index on your root. Okay, letter C, what do we got? We got the cubic root of a to the 9th over b to the 6th. Well, again, right now that doesn't make much sense to me. So what I'm going to do is I'm going to convert the problem to fraction exponents. So my exponent is 9, my root is 3. On the bottom, my exponent is 6, and my root is 3. So look what I have on top. 9/3, well, that's just a to the third. And on the bottom, 6/3, well, that's just b to the second. Okay, and the last one. We got a lot of stuff going on here, and just like before, we match up the like bases and try to deal with them. So I'm looking at this, and I'm dealing with my big numbers first. 42 divided by 6 is going to give me a 7 on top. I'm going to let this be my fraction bar here. I've got an x to the 4th on top and an x to the 3/2 on the bottom. I'm going to subtract, so 4 minus 3/2, which is 1 1/2. So 4 minus 1 1/2 is 2 1/2, but I can't write 2 1/2 in an exponent, so that's why I have to write 5/2. Then I have a z to the 7th on top, a z to the 5th on the bottom, so overall I have z to the 2nd. And so that's done, the x's are done, the x's are done. The only thing left is that y to the -3, Well, that can move to the top, so it becomes y to the positive 3. And you are done as long as you have no roots in the bottom and you have no negative exponents, which is what we have right here, so we can leave it there at that answer. Alrighty, another simplifying. Well, let's see. We have the fourth root of a to the second over b to the sixth. All right, these are a little bit more of a challenge because we have the fourth root of a to the second over the fourth root of b to the sixth. And it's a little bit harder to figure out how you're going to rationalize it when you're doing letters, but we can do it. Remember, we need to make a perfect power of 4. So a perfect power of 4 would be b to the fourth, because that would be 4 over 4. Or b to the 8th, because that would be 8 over 4. Or b to the 12th, because that would be 12 over 4. Any of those would come out to be whole number exponents. So I already have a b to the 6th, so what I'm going to do is I'm going to multiply the top and the bottom by the fourth root of b to the second. And then the top, I have to do the fourth root of b to the second. Now, the reason I chose b to the second is because that's what's going to turn that bottom into b to the 8th. And I can take the fourth root of b to the 8th. The top, let's see, what do I have? Now, these are both an index of 4, all right? And we're multiplying. So can we put those together? Yes, because we're multiplying. So our top is the fourth root of a to the second, b to the second. So let's simplify this. The fourth root of b to the 8th. Well, remember, that's just b to the 8 over 4. Well, that gives us b squared, and the bottom's done. Mission accomplished. We have no fraction exponents or roots left on the bottom. Now, our top, it looks complicated, but it's okay. We can write it one of two ways. We can write it as the fourth root of a squared b squared, or we could write a to the 1/2 times b to the 1/2. Either of those answers are fine. All right, one more. Now we're back to adding and subtracting, but sometimes you have to simplify the root before you add and subtract. In this case, we have 10 apples minus 6 apples, because the apples look identical. That means we have 4 apples. Not so bad. In the next one, we have a squared, b to the fourth. Here we have a squared, b to the fourth. So, looks like we have apples compared to apples. They're exactly the same. So if we have 3 there plus 4 there, well, that means we have 7, but they're still apples. Don't start adding your exponents, not when you're adding like terms. Okay, and then finally, these last two, the video's getting long. I'm going to show you the answer. 2x squared y z to the third times the cubic root of xz squared. If you have trouble getting that at all, make these all a fraction, and you'll fall out right away. Okay, the next one, we have 3, and then if you simplify both of these, you would get a cubic root of 2a squared. You know what, I'm going to take a little bit of time back on this number 5 now that I think about it, because this is going to cause you some troubles. Remember, if you get stuck, write everything with a fraction exponent. So we need the third root of 8. I usually don't write a fraction when I have the whole number as a base, but I like to when I have letters. X to the 7/3, y to the 3/3, z to the 11/3. That's what you really have in that problem. They're all multiplying each other because there's no plus signs between here. Okay, so the third root of 8 is 2. Now, let's think about this x to the 7/3. Well, 7/3, that's an improper fraction. But I can get some of the x out of there because how many times does 3 go into 7? It goes in there 2 times, and I have a leftover of 1/3. So a 1/3 x, that would be the cubic root of x. That's what's left over. Now, let's do the same thing with the y. 3 divided by 3 is 1, so I have y to the 1 out here. There was no left over, so there isn't any root I need to take. Z, 3 goes into 11, let's see, what is it, 3 times, that'd be 9. How much is left over? 2. So you have to have 2 left under the roof because it would be 2/3, and that's what Z squared cubic root means. That's how that answer came about. You're probably going to have to replay that once or twice because that's probably the hardest thing in the whole lesson. So do that if you need to. Your assignment is your worksheet and your practice quiz, 427. I'll answer questions before we start the quiz on Friday, but we won't have a ton of time. So make sure you get as much of this done as possible, and all of your homework is due before you leave me on Friday. All right, I'll be in at noon if you have any questions. See you tomorrow.